Hello students, welcome back. In the previous part we have learned about determinants. Today we will be learning about inverse of a matrix. Now we will be moving forward towards the operations on matrices, that how matrices are used and calculated. So let's get started. The topic is inverse of a matrix. Okay. Now for a square matrix A, the inverse is written as A inverse, where A is multiplied by A inverse. The result is the identity matrix. Non-square matrices do not have inverses. Now when we are talking about inverses is only calculated for a square matrix. It's not calculated for a non-square matrix. A non-square matrix means it will be a rectangular matrix. Okay, a square matrix is those matrices that have same rows and same columns. So this is the way you represent A inverse. A we minus 1, it's written as A inverse, it's pronounced as A inverse. Now the thing written out here, when A multiplied by A inverse, the result is the identity matrix. That actually means that, let's say we have a matrix A, okay, and you find out its inverse, that is A inverse. If we multiply A and A inverse together, we need to get an identity matrix. Let's say if we don't get any identity matrix in result, that means that the inverse is calculated wrong. The calculation done in inverse is not correct. Okay, so this is symbolically the representations. Okay, now the methods of finding inverses. Okay, the method we are going to discuss are adjoint method, Gauss-Jordan method. Okay, so these were the two methods that we are going to discuss how to find inverses using these two methods. Okay, so first of all we will be learning how to find inverse of a matrix by adjoint method. Okay, now I've taken a 2 by 2 matrix. A 2 by 2 matrix means a 2 row and 2 column matrix. Okay, so that matrix A has elements 3, -1, 4 and 6. Now this is basically the main formula for finding out the inverse. Okay, when we are specially doing it with the help of adjoint method. Now the formula for A inverse is adjoint of A divided by, now this symbol we are very familiar with it, it's known as the determinant of that matrix. Now out here I need to tell you this, that previously when I was talking about the determinants should not be equal to 0 if there's a non-singular matrix. If there's a singular matrix, you're not going to proceed further. Now this is the main reason out here. Let's say if the determinant of this particular matrix is 0, so anything divided by 0 tends to infinity, and we usually don't proceed further when there is 0 in the denominator. Okay, so whenever we are doing some sort of calculation, we need to make sure that the denominator should not be equal to 0. It should be any number but not 0. Okay, because anything divided by 0 is equals to infinity. Okay, now first of all we need to find out its determinant. As I said earlier that while we were doing determinants as well, that we need to calculate determinant whenever we are doing further calculations. Okay, so out here the first thing that we are going to do is to find out its determinant. Let's say if the determinant is 0, then we don't need to calculate the adjoint and finding out the inverse and all. Okay, so first thing is that you need to know that determinant is a non-singular matrix. Its determinant is not equals to 0. Okay, so determinant, now how to calculate the determinant? Determinant is that we just cross multiply these product minus in between, and we multiply these two elements in cross, right? So 3 multiplied by 6 minus in between -1 multiplied by 4. Okay, so 3 6 are 18. Okay, minus into minus gives us plus, and 1 into 4 is 4. So 18 plus 4 is equals to 22. Now since it is a non-singular matrix, that means we can proceed further to find out inverse of a matrix. Okay, now first of all, adjoint of A. Now how to calculate the adjoint of A when you're dealing especially with a 2 by 2 matrix, that is a 2 row 2 column matrix. For adjoint of a matrix, what we used to do, now See, this was my main matrix, right? The elements were 3, -1, 4 and 6. Now when we need to find out adjoint of a 2 by 2 matrix, the method is that you are going to swap the position of these principal axis, okay? So 3 was initially at this position, that is first row first column, and 6 was at second row second column. We're going to swap its position. Now it will be 6 and 3. Initially it was 3 6, now it will be 6 and 3. And what we are going to do further with the off diagonal elements, we will be changing its sign. Let's say now this was -1, so for adjoint of A this will be +1. Okay, this was +4, for adjoint it will be -4. So let's just go through it again, that if we need to find out the determinant, if we need to find out the adjoint of a 2 by 2 matrix, now this method applies only for 2 by 2 matrix, that is a 2 row 2 column matrix. What we do is that this is my main matrix, okay, I'm going to swap the position for diagonal elements, that is 3 and 6. For adjoint it will be 6 and 3, and for the off diagonal elements what I'm going to do is that I'm going to change its sign. Now initially it was -1, in my adjoint A it will be +1. This was +4, in my adjoint it will be -4. That is how you calculate adjoint of A. Since we have calculated adjoint of A and we have also calculated determinant of A, so now what we are going to do, we are going to substitute these two things in this formula. Okay, so that is how you do it. Okay, you write it like this, or you just divide it by 22, both mean same. Okay, now see, we have learned in operations related to matrices that if any scalar multiply with a matrix, what happens? Okay, so that particular scalar multiply with every element of the matrix. So this scalar, this is a scalar quantity, is multiplied by all the elements. Now you divide it by 22 like this, or you just write it down by 1 by 22, both mean same, right? So 6 divided by 22, 1 divided by 22, -4 divided by 22, 3 divided by 22. As you can see, the formula we have was adjoint of A, that means this matrix divided by the determinant of A. That means you're going to divide each and element of this matrix by A. You're going to divide each and every element of this matrix by its determinant. Okay, so what we did out here, that 6 divided by 22. Now what I've done here is that I've just simplified it. 6 by 22 is 3 by 11. 1 by 22 minus 4 by 22 is -2 by 11. 3 by 22 is 3 by 2 as it is. Okay, so this was my final answer. Moving on, the property that I told you earlier, that if we need to check that our determinant is right or not, what we are going to do is that if you multiply inverse with its own matrix, the inverse, that is, this was my initial matrix, matrix A, and this was the inverse that I calculated. Now what I'm going to do is that if I multiply these two matrices, the result will be an identity matrix, and that is somehow, you can say, the clarification for our inverse. That is correct. We just multiply A by A inverse. Is basically a property that if you multiply A with A inverse, the result should be an identity matrix. If the result is not an identity matrix, that means the inverse that you have calculated is not correct. Okay, so as you can see out here, I have just multiplied matrices. Now how to multiply two matrices, I have explained it earlier. I'm just going to give it a rapid go through. That what we do is we multiply row by columns. Okay, so that row into column is the multiplication rule for matrices. First row with first column, first row with second column, second row with first column, second row with second column. Okay, so this is how you multiply a matrix. That is 3 multiplied by 3 by 11. The sign in between is plus, -1 multiplied by -2 by 11. So this will be my first element. Then 3 multiplied by 1 by 3 multiplied by 1 by 22. Okay, this is the 1. 3 multiplied by 1 by 22. I've done a mistake here. It's 22. 3 multiplied by 1 by 22 plus minus 1 multiplied by 3 by 22. Okay, so same goes for second row, first column. These are the multiplications, and if you just simplify it, you'll get an identity matrix. Okay, so which verified that the inverse that we have calculated is correct. Moving on, now we're going to take an example that has 3 rows, a square matrix of 3 rows and 3 columns. So you can say a square matrix of order 3. Okay, order 3 means 3 rows 3 columns, right? So the formula remains same for both. Okay, it's A inverse is equals to adjoint of A divided by determinant of A. Now what I have done here is I've already calculated its determinant, which is equals to 31. Now I want you all to calculate its determinant on your own and verify this, that is it the determinant of a 3 by 3 matrix is 31 or not. Okay, now how to calculate determinant is, this is what something I have explained in my previous part, so you can go and check there how to calculate a determinant. Since it is a non-singular matrix, that means you can know further, we can proceed with our adjoint further. Okay, now how to calculate the adjoint of a 3 by 3 matrix. Now we have seen calculating adjoint of a 2 by 2 matrix is comparatively easy. Okay, just need to swap the diagonal positions and we just need to change the signs of diagonal elements. But for 3 by 3 matrix, adjoint is it's different. It's calculated differently. Now how it is calculated? Okay, so first step is that we need to find out the cofactors of A. Cofactors means that all the elements involved in a matrix. Okay, so we need to find out each and every factor of that A. Okay, now we know that a matrix A, that was a 3 by 3 matrix, has 9 elements in total, right? So there will be 9 cofactors. Now how to calculate that factor? Okay, the first thing is that we need to calculate A11. So 11 means what? 11 means first row and first column. Okay, is equals to, now out here you can see I've written a sign plus. Now what you can do is that you can go alternative, we'll go alternative sign. Okay, see, this was my initial matrix. Okay, for A11 plus minus plus minus plus minus plus minus plus. So this is how we go alternatively when we are dealing with signs and adjoint. Okay, now for cofactors, as it says first row first column A11, when we are finding cofactor for this element, first row first column, that means we need to hide first row first column, and this is my remaining elements, which is now converted in 2 by 2 matrix. Okay, see, these are the cofactors. Now how I get this minus 1 is like finding out the determinant. Okay, so it's like 2 into 2 4 minus in between 5 into 1 minus 1. Okay, now let's calculate it for A12. For A12 means you need to hide first row and first column, second column. Remaining elements will be 0, 1, minus 4. What we have done here is that we just multiply these two elements with these two elements. The remaining I got is 4 and minus. Why minus? Because this minus is multiplied with this number. Now we're going to do it the same thing with the A13. Now first row third column, hide all the elements of first row and third column. The remaining elements will be the cofactor for A13. Now 0 into 5 is 0. Positive 2 into minus 4 is positive 8. Positive into positive is positive. Now for this A21, minus 2 into 2, that is minus 4. Sign in between will be minus. 3 5s are 15. Minus 4 minus 15 is minus 19, and this minus is also multiplied with this number. So minus into minus plus. A22, 1 into 2 minus 3 into minus 4, that is minus 12. So 2 minus minus plus, 2 plus 12 is 14. Plus into plus is plus. So as we are doing the same thing with the A23, that is 1 into 5 is 5. 2, 3 means second row, third column. 1 into 5, 5. Minus minus plus, 4 2s are 8. So 5 minus 8 is minus 3. And since minus is multiplied with minus 3, so minus minus cancel, the result is positive 3. We're going to do the same thing for A31, A32 and A33. So these are the results that we got by the end. So okay, now the next thing is that the second step for calculating adjoint is the moment you get all these numbers, that is okay, this 2 1 2 2 2 3 3 1 3 2 3 3, the next step is that you're going to place all these number in their own positions. Like for minus 1, for A11 the result was minus 1, here is minus 1. A22, A12 minus 4, A13 8, and so on. Okay, next step is the moment you place all these number at its positions, you're gonna take its transpose. Okay, you're gonna take the transpose. It is an important part that you need to take transpose after you just plug in all the cofactors. Okay, so when I take the transpose, now what exactly transpose is? Transpose is basically converting rows into column. Okay, so this was initially my first row, now it will be my first column. This is my second row, it will be my second column. This is my third row, now it will be my third column. 1, see, minus 1 minus 4 8, minus 1 minus 4 8, it's now converted into my first column. Okay, the next and final step is what I have done out here, that I have divided every element of this. I've just substituted everything which I have calculated into the formula, that is A inverse is equals to adjoint of A divided by determinant of A. And at the end what I have done here, just I've divided each and every element of this particular matrix with 31. So this is what the final answer that I got. Now for verification, what I'm going to do is, then I'm going to multiply A with A inverse. Okay, so multiplication rules is same. You just multiply row with column, first row, third column, then second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. This is how you multiply it, and you just verify your answer. Okay guys, earlier we have learned how to find out inverse by using adjoint method. Now we will be learning how to find out inverse by using Gauss-Jordan method. Okay, now for Gauss-Jordan method, what we are going to do is, out here I have used the same example as I have used for adjoint method. Okay, so the method for Gauss-Jordan is that we will be separating, we will be applying operation on these two parts. Now this line is basically called the augmented line. Okay, now augmented means that if you introduce constant into a matrix, that is what we call an augmented matrix. And out here we have I've just introduced an augmented line, and after my augmented line I've written an identity matrix. Okay, now out at this side, as you can see on the left side, I have written matrix A as it is, and on the right side is my identity matrix. Now since this matrix is an order 3 matrix, that is a 3 row 3 column matrix, so this part of the matrix will also be a 3 by 3 identity matrix. Okay, the steps involves that we will be converting this part into an identity matrix, and we're going to perform the same operations that are used to convert this into an identity matrix to this part. The result will be that at the end this part will be converted into an identity matrix, and this augmented line, the matrix which is written after the augmented line, will now be converted into the inverse of the matrix. This will be automatically converted into the inverse. Okay, let's get started. Now first of all, as you can see earlier, For in order to convert this part into an identity matrix, the first thing is that this pivot position should be equal to 1, which is already 1, and the elements below this pivot position should be equal to 0. Now this second element is equals to 0, but this third element is minus 4. So that means we need to convert this minus 4 into 0. Now the operation required to convert this minus 4 into 0 is R3 plus 4 of R1. Okay, so if I just take this minus 4 plus just multiply this number 1 with 4 and add them together, the result is that I'll get this element removed and this will now be equal to 0. Okay, now I need to perform this operation on this whole row, okay, on this complete row. So 5, that is the second element, third row element, 5 plus 4 times of R1, that is minus 2, is equals to 5 plus minus 8, that is results will give you minus 3. And finally 2 plus 4 times into 3 is 2 plus 12, that is 14. See, it's now 0. These two elements are also changed. Now the same thing I'm going to apply on this side of the matrix. Here you get, see, these two elements will have no change, and so as this, the only element will be changed here will be this one. Okay, next is that I need to, if you can just look at the matrix once again, now I need this pivot point to be equal to 1, pivot position to be 1, and all the element above and below this element should be 0. Now first of all I need to convert this, and for unit matrix it is important that the diagonal elements are equal to 1. So this has to be 1. Okay, so the operation required is R2 multiplied by 1 by 2. So what will happen is that if I just multiply this second row by 1 by 2, I will get something like this. This has now converted into 1, 1 by 2, 0, 1 by 2 and 0. Okay, now the condition is that we need to make the this element, if since this is 1, now we need to make the upper and lower element here in this column equals to 0. So first of all we are starting with this minus 2 first. Okay, so how we convert this minus 2 into 0? The operation required is R1 plus 2 times of R2. Now R1 is minus 2 plus 2 into 2 is 0. Okay, so this will be 0. And for this number, 3 plus 2 times of 1 by 2 is equals to 3 plus 1, that is equals to 4. So this is how it is done. Now you can see 1 0 0 0 1 4 1 by 2 minus 3 14. This part I have written it as it is. I will be performing operation here. See, 0 plus the same operation, that is the same operations that I have applied. Okay, R2 plus 2 times of R1 plus 2 times of R2. So R1 plus 2 times of R2 will be 1. So as you can see, it's 1. Okay, then we need to make this element equals to 0. Now for this element to be equal to 0, the operation required is R3 plus 3 times of R2. Now for R3 plus 3 times of R2, this has become 0. Okay, what will be this? This is 14 plus 3 times into 4, or sorry, 14 plus 3 times multiplied by 1 by 2 which will give you 2. Okay, now we have done the same thing on the other side of the matrix as well, and this part has now converted into 3 by 2. This will remain as it is. Why? Because it's 0 out here. Okay, so anything add or subtract with 0 remains as it is. So 0, initially R3 out here was 0, plus 3 times of R2, that is 3 into 1 by 2, which gives you 3 by 2. So here it is written. Then As you can see that now we are very close to our final answers. We need to convert this number, the diagonal element, that my final number, this number into 1. For that, the operation required is, if I just take its multiplicative inverse, okay, so it will be 1. So R3 multiply by, this is 31 by 2, we will multiply it by 2 by 31. If you just multiply this complete row with 2 by 31, so this is what we get, okay. This is my 1, this is 8 by 31, 3 by 31 and 2 by 31. Now all these diagonal entries are 1. Pivot position was 1, all the entries below pivot position is 0. This is my pivot position, above and below entry 0. This is my pivot position, and all the entries above out here should be equal to 0. Now the first operation that we're going to convert is, we're going to make this element into 0. Okay, so what are the operations required? R2 plus bracket minus 1 by 2 into R3. So I've just multiplied R3 by minus 1 by 2, okay, and I will be adding it into the second row. The result will be that this element will now become 0. There you go. Okay, same as for the other side of the matrix. Okay, now you can see I have applied, let me go just further back. For the second part, that is for this part, okay, for this part I have to apply R2 plus minus of 1 by 2 R3 onto this side and this side. All three entries will now be changed. Now how they will be changed? See, first entry, then this one, then this one, okay. So it was my second row first column, second row second column, second row third column. So this is how it's now changed. The final answer that I got is this. Now for this side of the matrix to be converted into an identity matrix, it is important that this should also be equals to 0. So operation required is R1 plus minus 4 times of R3. See, this is now equals to 0, and I'm going to apply the same operations on these three elements as well, okay. And I've applied operations on these three elements as well. This is what my final answer is. 1 by 31, 19 by 31, minus 8 by 31, minus 4 by 31, 14 by 31, minus 1 by 31, 8 by 31, 3 by 21 and 2 by 31. Okay, so this is how you get your final answer with the help of Gauss-Jordan elimination. Now you can use either of the method. Most preferable methods we use is Gauss-Jordan method, because it can solve a bigger system as well, not only 3 by 3 but 4 by 4 and so on. And it is comparatively easy as compared to adjoint method, because when it comes to adjoint of a higher order matrix, it becomes more difficult and complex. So this is all for this part. I hope you have understood how to find out inverse of a matrix by using adjoint method and by using Gauss-Jordan method. I'll see you in the next part, where we will be learning about how to solve system of linear equations. Thank you so much.